The conclusion of this presentation will be that different than in many other examples that you have heard already in this symposium and that you might hear later, in fMRI, motion is not such a showstopper. In fact, I actually want to claim in this presentation that high-resolution fMRI might actually be a solution to head motion, as opposed to low-resolution or other forms of imaging. And I have no financial interest to disclose with respect to this presentation. First, let's be clear what I mean with high-resolution fMRI. I mean this emerging research field that's out there since quite a while, a decade or so, that is you looking at sub-millimeter laminar and columnar fMRI in living humans. And it's exploding right now and growing a lot because there has been more evidence that it might be useful for application studies. And the application studies where it's mostly applied to are kind of basic cognitive neuroscience questions on looking at layers mostly. And in those kind of studies, we have the luxury that we are mostly looking at participants that are healthy, well-trained, and compliant compared to other subdisciplines. And while this field has technical challenges, I think head motion is not the most often discussed one. So among the 250 papers that are published to date already, only 3 of them actually focus on head motion. So it's kind of weird. Is motion not an issue then? Vice versa too. Not only does high-resolution fMRI academic literature not care about motion that much, the motion correction field also doesn't really care so much about the high-resolution fMRI field either. It was not part of any of the ISMRM workshops that were recently planned. So this very symposium is now the first motion correction event that puts attention also to the field of high-resolution fMRI. And this disconnect between the different fields is kind of strange, isn't it? So in high-resolution fMRI, people care about very, very small things. Like in this example for a tapping experiment, we care about these small voxels kind of following the cortical ribbon that I would like to interpret as layers, or also these kind of columnar vessel-like looking structures over there. And those are tiny structures. They are as small as like less than a millimeter. So how can we get high-resolution data when the original data from like in the underlay, you see the EPI, and this is basically an average of kind of the original data looking like here for the most extreme case in the entire time series. So you see that there's a lot of motion happening, but still, I think the difference to conventional other methods of imaging, not fMRI method, is that in fMRI, we're looking at dynamics. So even in this example, I would claim that the motion within the individual images is actually quite small. In fact, the motion that we are seeing here is motion across different TRs, which is a different form of motion that other fields are very often limited by. So usually when you have those kind of data, you can, in retrospect, kind of align those data to make them more stable. And then, for example, end up with a time series looking like that. And my computer is a bit at the edge with the resolution here. There you can see that it looks much more stable. However, there are still kind of these instabilities visible, which then are not only referring to inter-TR motion, but also motion within the TR, which in 2D methods can refer to kind of spin history effects, or in 3D or multi-shot methods, like in this example, those are more kind of phase inconsistencies across the different parts of the K-space as they're acquired. So, and in those examples, it is quite common then also to use censoring, so to detect these motion spikes and then censor them and exclude them from the functional analysis later. So you end up with a time series looking like that on the right here, even though the original data had kind of significant motion in there. So in fMRI, as long as people don't move kind of constantly, which like all the time movement, which I've never really seen, motion-related dropouts of entire data sets are usually negligible in the range of like 10–20% of a study. So let's look a bit into the details here. How is this retrospective motion correction done? And usually this consists of 2 steps. First, there's the motion estimation, and then there's the image correction. So let's look at the motion estimation and how high resolution can benefit here. And there's one specific study from Wang et al. From the Jonathan Polimeni group, and also Anna Rose group, that had kind of ground truth motion at a high resolution data set, and then downsampled the data successively, subsequently, to look at the motion traces. And it turns out that the higher the resolution, the most accurately you can detect the motion. The lower the resolution, kind of the more you underestimate the motion traces. So basically telling us that high resolution helps you with the motion estimate. The highest the resolution, the smallest the residual error of the motion, still existing though. The second part in the motion correction then would be the image correction. This means that as soon as you know the motion, you need to kind of resample the data. So in this cartoon model here, we assume that we have signal in a given voxel, and then with motion, we need to get it to a new spatial grid, for example, the blue spatial grid, which might be shifted, replaced. So now we need to transpose the signal from this original location to the new location, and this is usually done with some sort of kind of a weighted averaging of the voxels around it, interpolation. As shown in this little animation here, when you have this voxel that kind of moves around, you can see that in the sampled object, now we have kind of signal that is distributed across many voxels. We can never have higher resolution than our voxel size. And after motion correction, the signal still stays at the location where it should be, but you see these kind of interpolation smearing effects. And again, if here also for image correction, resolution helps. For example, if you just zero fill your original data or upsample them, or just acquire them at higher spatial resolution, you can see that that the sampled object has less of these kind of edge effects. And on the very right, you see that the location is now at the position where it should be, and we have less of these kind of blurring effects. And these kind of blurrings and spatial interpolations is not really something that's specific to motion. It's something that we need to do anyway in high resolution fMRI, for example, due to geometric distortions or due to gradient nonlinearity corrections or structure function alignment. So motion is just adding one additional matrix into this analysis pipeline. And it has been established that it's most beneficial to combine all the different spatial concatenations into one matrix and do only one resampling step at the end. So next, I would like to show you some extreme examples where motion correction, where head motion in high resolution fMRI can be, in fact, really annoying. And in some of those cases, they can be maybe even a showstopper. So here are a few examples that I want to go through. Starting with this example, where we are looking at conventional SLAB protocol, which is usually acquired for high resolution fMRI. And you can see here the motion across different runs in a time series of 90 minutes. And you can see that there's a lot of motion happening. It could be better. I think it could be worse. Overall, I think this example is about representative. And if I, just as a reference, take all these data, average them across all the runs, all the time points, I get kind of images like down there, especially also in the front of the brain that usually moves the most. And maybe the first message I want to bring across here is that you can see that it's blurry because we didn't correct for anything, but also you can see that there is some structure remaining, right? So it's not that everything's lost. So for example, the voxel up there might not always capture the superficial layers across the entire time series, probably not, but still the probability that this voxel is capturing superficial layers is higher than, for example, that voxel that most probably has the deeper layers within that spatial grid. So it's not entirely kind of, if motion correction doesn't work perfectly, there's still some signal you might harvest at the end with differential analyses. So now if I pump those data through a conventional pipeline that might be optimized for whole brain conventional imaging, you can see that it tries to do its best within the slice. But as soon as you look at the kind of coronal or sagittal slices, the brain is kind of still moving up and down a bit. And this is partly coming from the fact that we're looking at SLAB data here. So in 2D acquisitions, the outermost slices have different spin history effects due to different kind of slice leakage effects. In 3D acquisitions, you have the similar effects, maybe even stronger due to imperfect SLAB excitation profiles. So you still don't really correct for this kind of within SLAB motion. If you can account for this with a bit of tweaking of using locally optimized motion estimation, for example, using masks that optimize the slices within the middle slices, not as much as the outermost slices. And then you can see that now the brain is stable and it's just the borderlines that move up and down. And you can get a lot of the spatial features back without these kind of edge enhancements artifacts here. And this kind of trick of using a locally restricted motion estimation can also be helpful in other forms of motion. For example, in nonlinear motion, like in this example, where the motion has been optimized for the motor cortex over there. And then you see that there are still parts of the brain or the scalp, in fact, that seem to move around. So it might make sense to really optimize the motion correction to the area of interest. And while this trick of local motion estimation restriction is very helpful in some cases, it's not sufficient in other cases. For example, in this one, where we are looking at low bandwidth EPI readouts, as we always use and need to use for high resolution EPI. So we are more sensitive to these B0 geometric distortions. And you can see that there's quite a lot of kind of nonlinear motion going on, because very often in layer fMRI and high-resolution fMRI, we are limited by SNR. So we need to average not only across many runs, but sometimes even across many sessions. And the motion across different sessions is obviously much stronger than the motion across different runs or TRs. And in those cases, it can be helpful to also consider these nonlinear alignments, for example, the Arndt-Syn algorithm, which can put the voxels back in the location where they should be. And then even across different days, you get very stable activities. You just have these residual kind of shading patterns, like these fuzzy ripples, we call them, moving across the brain. And if you don't like them, you can also use kind of a multi-contrast imaging like ASL or VASO in this case, or even use a multipolarity readout approach that you can learn more about on Tuesday. While these nonlinear motion alignments can be helpful for high-resolution fMRI, they also have their limits. They're not only very computationally expensive, but also they need to be constrained to the right spatial scale, which I would like to explain in this little example here, where we have a very strong activity, a finger tapping task with a block design, and then it's strong enough that you can even see directly in this hand knob over here that we have kind of rest, dark, bright activity, rest, dark, bright activity. And I think you can also see it on the screen. Like there's a strong signal change, which is the signal change that we are interested in fMRI. And now if I use a nonlinear motion estimation here, you can see that the algorithm, the model, alignment model, misinterprets these signal changes as warping and then tries to account for this and remove some of the variants that we care about, and basically tries to warp right in activity of interest. So you need to watch out about these kind of nonlinear algorithms and apply them at the right spatial scale. Let's go to even harder cases. For example, this slide from Tyler Morgan about line scanning, where she's interested in these single virtual electrodes that are aligned perpendicular to the cortex at very, very high spatial resolution, also temporal resolution. And the placement of this line then poses challenges and needs some logistical framework around it. So in the first session, she acquires a structural scan to find then the best location of the line placement with a respective parametrization of that line in that frame of reference. And then in the second session, there's a 1-minute structural localizer, which is offline aligned to the first session to spit out the coordinates that you can then type into the protocol editor from Siemens and then have the line in the right space. But you can also not only do this across different sessions, but also, for example, across different runs, as shown in this example on a slide from Paul and Divya, that are streaming data in a socket-based approach with their own kind of raw data sender, then aligning it and using a Scout hijack sequence to basically override the Scout matrices of the scanner, because there is a framework from the vendors already to align based on the Scout, and then hijacking this to align this very 2D slice and have it at the same location across all the different runs to do these very high resolution individual vessel single slice fMRI. Not only across different sessions or across different runs, but there are also advanced approaches of aligning the field of view on a TR by TR basis, commonly known as a prospective motion correction. Here, for example, using FAT navigators in this approach from Dr. Raimondo for layer-specific line scanning and really taking good care of these motion spikes over there. Or with camera-based approaches like the one that we might have heard about already from Oliver Speck in the first lecture, limiting the kind of residual motion in these high-resolution fMRI data, as shown from Jonas Bause. Maybe even harder examples of high-resolution harder examples of motion in high-resolution fMRI refer to task-correlated motion. Like here, this is a very hard engaging task where participants are asked to do a mental alphabetization task. And during these periods of the black arrows, these are the most intense periods of the task. And then the participants, they focus so much that they almost forget how to breathe. So here we're looking at the respiration curves. And then sometimes, even after the task, they take a deep breath of relief. And then when you look at the activation maps, you have these kind of EPI artifacts that are task logs. And there's kind of little you can do about that. Still, you can try to untangle the time of the task-locked motion artifacts that are manifested instantly in the EPI space and EPI images, as opposed to the HRF that's kind of delayed and a few seconds later. So you might be able to tease that apart with a different timing, or you maybe have some hope still that you can reduce some of this variance by not looking at the main effect, but looking at task differences across the different black arrows. But at the end of the day, if you have task-correlated motion, your data will never be as clean as you want them to be. I think the single most common issue of motion that I'm exposed to in high-resolution fMRI is not really referring to motion of the fMRI data itself, but more of motion with respect to the reference data that we need to analyze the fMRI data later. For example, looking at motion in the 10-minute MP2 rate scan that many people use in layer-dependent fMRI. And it's just much more likely that people move at one point during those 10 minutes it's not so likely that they move like within any given TR of their fMRI time series. And the mitigation strategy that I found has great potential here is the approach developed and shown at this conference from Kenny Chung, namely using MP2 rates with a 3D EPI readout, which is much more efficient. And then you have many, many averages where you can see in the movie down there across the different repetitions that some of the repetitions are then motion corrupted. And because you have many repetitions, you can basically sort it out, censor them, and still have kind of retrospectively aligned and censored a nice whole brain structural scans that you can pump through FreeSurfer, for example. And because 3D EPI is so efficient that you can effectively get a whole volume in 20 seconds, you're actually approaching the time scale of fMRI. So this gives us a window to look at a new form of motion contamination in fMRI, in high-resolution fMRI. Namely, you can basically do your fMRI task right during your structural scans. Here, for example, a flickering checkerboard, where you use the second inversion of the MP2 range to feed in to the bold models and the uni image to give it to FreeSurfer. And then FreeSurfer interprets these T1 changes during activity as an expansion of gray matter. So it looks like during this checkerboard, gray matter is expanding, and it's mostly the gray matter white matter border that seems to move, not so much the gray matter CSF border. As you can see on the bottom left here, which is only located in the visual system, in the frontal areas and control areas that are not believed to be a lot engaged during this visual task, you can get an estimate of the stability of these kind of borderline surface estimates, and there are no clear kind of shifts over there. And there's a bit of literature on task-based structural changes, but there's very little established knowledge on the impact of these effects on high-resolution fMRI. So most researchers so far basically just ignore it. After having talked about many things that can be annoying with head motion in high-resolution fMRI, let's also talk about a few things that are not as annoying as expected. For example, there are very scary data out there. For example, NIH director and themselves, they tweet images like that, where they call the brain, quote unquote, a moving organ, which I think can be kind of misleading. So they have this amplified motion models where on the right here, you see that basically the entire brain warps and it's kind of stuck. Which could tell me as high-resolution fMRI researcher that it's impossible to do high-resolution fMRI at that spatial scale down there. When you look at the Wikipedia page of CSF, you can see that it doesn't really look like moving so much, but still kind of it looks like there's so much variance that any fMRI will be hopeless. Let's just look at it with a conventional protocol of high-resolution fMRI here, a segmented 3D EPI, where you can see in the movie here that there's some motion going on. For example, down there, there's a lot of signal fluctuations. I hope you can see this, maybe up there. So there's like CSF indeed moves a lot. And to make this a bit clearer, I kind of looked at the cardiac cycles, and then you can see the movie over here, which are the areas that show a lot of signal changes across the cardiac cycle. And you can see there's a lot going on. The vessels over here show things, CSF is rushing around. But if you look closely, the brainstem itself does not seem to be like moving a thing, right? There are these very fine scale structures that are not blurred at all. There are these kind of tiny vessels. So if the brain stem is moving, it's not moving as much as people are feared. If you increase the echo time a bit more with that, you can even see more of the CSF kind of flushing through, even going to the sulcal CSF space. So there is a lot of motion, CSF motion. The amount of tissue motion, I think, is not as bad as people are afraid of. And again, resolution helps. So with high resolution, we keep the CSF motion in the voxels where it should stay outside our tissue, so we can still look inside the tissue on functional activations. Another thing that I think is not as bad as people feared is motion across multi-shot sequences. For example, the very popular 3D EPI for high-resolution fMRI, which I would like to explain with this Valsalva task, which is a very intense task. It's a breath-holding task with chest pressure increase, and it's the most absurd task that I ever encountered. It has contrast to noise ratios like where you directly see the vessels for calibration, like with the naked eye. popping out at you. However, you also see that there's task-correlated motion, which is specifically visible looking at the motion traces here. And with conventional kind of 2D multiband approaches, this can be a problem. Like, because with multiband, you acquire slices consecutively. This means that slices that are very close to each other in space might be very far from each other in time. And this means that when you have kind of these inter-TR head motion, there you have these different spin history effects strongest at the border of the slices. So after motion correction, the brain is kind of now stable, but these kind of spin history effects are kind of moving. And this can impose for this kind of pitch motion and a bias, especially in the anterior-posterior domain. Now, in multi-shot methods, like for example in 3D EPI, we don't have these spin history effects as badly because we acquire the entire slab over and over and over again and just vary the different spatial frequency weights. And then this kind of inter-TR motion can be kind of accounted for retrospectively to have the stable brain. And then looking at a given slice, you can see that we don't have this anterior-posterior bias and can tease out the vessels a bit cleaner. They're still there, but they're kind of overlaid. And this is again referring to inter-TR motion. Within TR motion, we'll have other issues. Finally, as we will learn also from David Carmichael in the last lecture of the symposium, prevention is better than cure. And I think, again, in high-resolution fMRI, we are a bit privileged here. Namely that in most fMRI studies, we just have the luxury that we blacklist participants who cannot lie perfectly still. And we just never invite them again, ever. Also, I found it helpful to let them watch their favorite show. They move less. And I also learned this from my kids, that give them something to watch and they will sit like a statue. And even though there's scientific evidence that this reduces motion and improves data quality, I still could not convince my employer, NIH, to give me and buy me a Netflix account. And it's also only limited to very few functional studies. Most people that I like, most people around me that do layer-dependent fMRI like these inflatable cushions. That kind of press the skull into the coil and restrict movements. But also I found it very, very helpful to provide feedback. If a person moved, tell them that they moved and tell them that you need to repeat the scan and that they will not get out early. This will really motivate them to lie as still as they can. There are also reports, a lot of reports and good experience with using medical tape to give the participants kind of haptic feedback if they move and to keep still across a long period of time. More extreme cases also include this bite bar, which is very effective. However, it's usually not the favorite approach for the participants. They don't like it so much. As soon as the abstracts are online, I might highlight a few of them. And in conclusion, I think motion in high-resolution fMRI can be annoying, but it's not the thing that's holding us back or that keeps us from going to high and high resolution. There is no vendor-provided solution available yet, so I think that again, in the future, motion will remain annoying and there will be 1-2 participants in every study that you need to exclude, but it's not the thing that's holding us back also in the future. And with this, I want to thank all the folks that provided material for these slides, and I thank you for your attention. All right. And we have a few chat things. This is a motion-enhanced image, often misquoted animation. It took 23 minutes. Okay, so I need feedback on what to cut. And wait, I'll make a screenshot of this. I think Farouk's comments is mostly referring, I will share my screen again. The motion amplified thing you're referring to this slide. Is that right, Farouk?
Yes, correct. This is a motion, like this comes from a motion amplification paper that they show if you amplify the motion using a specific algorithm, you can visibly see subtle motions. Whereas this animation, because it looks so nice and easy to attack to fMRI, is very often misquoted on Twitter. So maybe you should say that this is an enhanced image. Otherwise, you would propagate the same.
I mean, I'm trying to make a straw man here, and they kind of made it sensational and by showing it in that way. So yes, how do they call it? Like I think that's also the reason why there are 2 brains, right? The left one is the original, the right one is the amplified one.
I think you can save time to do this part quicker. Your point is that it's not a problem.
Right, or not as a bad problem as people are afraid of. I still think that the brainstem moves, but not as much as that. And
I
even
think
though
it's
it's
fine, but you could just, this
Right.
took you some time.
right. Okay. Is there anything else that could give me some time, or that you think was not really necessary or a distraction?
I think it's the great thing about the talk is it's comprehensive. Like, what about this? What about that? You can do everything.
Okay. Okay.
I think just maybe saying less with each topic.
Okay.
Like the nonlinear warping sometimes.
Okay. Thanks. I know that people have strong feelings about, like Ravi Menon, like on Twitter, if you mention it, he said, never ever do that. So I'm not sure if that's like what the field is thinking about it, if I should propose it at all with the kind of caveat that I'm mentioning, or if it's kind of too much out there. I like it.
But your conclusion is that it can remove task effects.
Yes, yes. If you apply it in the wrong spatial scale, like with the default of synth, then it kind of uses smaller and smaller kernels. If you like don't apply it, like going down to the smallest kernels, then you might not remove it that much.
The problem with talk is any part of it could be an entire talk.
Yes.
Right. I mean, you
Right.
can give a
Right.
And also,
can you show all of your slides?
Yes.
Like an overview view of the entire talk?
Sure. If you want to download them, you can grab it there.
No, more for thinking about what you could.
Okay.
I mean, I probably will want to download them, but
Okay, wait. And then I started again. Are you seeing my screen now? Yes.
yes, tiny little PowerPoint.
Okay. I think I will cut the bottom one and include the reference where it's from, because I'm not really talking about that on that slide.
I was thinking more of like the grid view where you can see each slide all in one.
Okay. I will show.
So think at the bottom.
Like the bottom right, there's a slide deck
Yeah.
indicator.
A little bit.
I don't know why I made it
Not
so
there.
small. Oh, there.
Oh,
Yeah,
yeah.
there.
Yeah, you can make it bigger.
Can you see enough to point?
Yes. This. Yeah. I just
Maybe.
wanted to
Yeah.
get the big picture and try and think about it, because I thought it was all it was all great and all useful.
Maybe part we were talking about sampling, you could condense that down
Okay.
into
Right.
because you have like 5 or 6 slides here,
Right.
and that I don't know, I mean, maybe it's not apparent, but to me that's an apparent win.
Right.
So you don't have to spend so much time.
I kind of felt like you talked about the breathing artifacts twice. I mean, you did, and they were separate ideas. Because there's what does the artifact look like? And then there's later also task-induced motion, 2D versus 3D. I don't know if those can be combined in some way, if that would be more efficient, because you're showing different things, even though it's both breathing cases.
Thanks. That's a good point. Yes. I mean, also the Valsalva thing is kind of not really that high resolution, so maybe it doesn't fit so much. But I think I need to talk about 2D, 3D a bit, because
I think that's important. Yeah.
Maybe I can use a different example.
I actually found the 3D discussion a little confusing.
Okay.
I'm gonna go with it. The idea is that motion will cause blurring for a 3D acquisition.
Within TR motion. So with the Valsalva thing, TR was very fast, so we only had a cross TR motion, and then had the spin history effects, which were issuing 2D but not 3D. The within TR has spin history effects in the 2D still, but then it also has like phase issues in the multi-shot, which can be blurring.
Delve into that.
Yeah. Well, I mean, if you want to, yeah, that, right. Yeah.
Right, that won't be evident in motion estimates. Right?
Correct. Yes, and you can also not correct for it anyway. Yeah.
Right.
Yeah.
If you want to cut something, I feel that maybe line scanning is not so much motion correction related, or maybe I didn't get like how it connects to motion correction.
Yes, I mean it's one of the few things where there is at all any like literature out there. So that's why I had it in there, but I can certainly condense it. It's maybe more a field of view prescription, less than motion. Like I talk about kind of intercession, which is in motion, or interrun, that's kind of motion, and then within runs.
Yeah, I mean you are 8 minutes over time, right? So
yeah, I need to cut. I need to cut.
something.
Yeah.
Yeah, kind of from the same perspective as Farouk. If you are going to include the line scanning stuff, I would at least put it kind of so slide 21 is really like kind of an introduction to slide 24. But I'm not even sure that I think the scout-based FOV prescription is a nicer example than what we were doing. We were kind of doing the primitive version of that stuff, so you could definitely cut something there.
I will mention your stuff too, but maybe we can kind of merge it in the same thing.
Yeah, I think that
Yeah.
makes sense. I mean, the goals are the exact same there. It's just what we were doing.
Okay, thanks. And also, like, this is due to the rescheduling relatively preliminary, so I think I can smooth it out and just make everything more efficient, and also cut a few minutes with that. And I think I have 20 minutes at the end. It's just if I want to have 5 minutes of questions, which I think I do want. Was there anything that you found too controversial, or where you don't think this is kind of the consensus in the field in high resolution fMRI? Because at the end, it shouldn't be about me. It should be more about the field of high resolution. And my stance is
there was one statement you made that bothered me. I think you qualified it and it was fine, but you said something. You were it's in the very beginning, slide 7. You're showing a cross TR motion, and you're saying, oh, they moved. You kind of said something like they moved between TRs, but it doesn't necessarily mean they moved within TRs. And I don't think that can be true.
No.
Your point about not moving continuously, obviously, it's fine. I think it was more the way you said it, because I feel like people say, "Oh, it's just like." Maybe in lower res land, I feel like I heard this a lot in grad school. You see someone, you're like, "Oh, they just move with it between the TRs, or it doesn't really matter." And being like, I feel like it kind of gives people the wrong impression,
Right.
because if they're moving from TR to TR, they have to move.
Right.
During a TR as well. You
Right.
can't get from A to B instantaneously.
Right. Yes, you're right. I
it was
can
just the way
I
you
can rephrase it. I guess
you
it's the
you
amount
asked
of
me to
motion. Yeah.
you asked
Yeah,
for something
thanks.
picky, so
Yeah, thanks. Appreciate
I
it.
wanted to be picky.
Yeah, and
But I do like that slide in general, because I think it is important to highlight your final. I think the final statement you said is they're not moving continuously. I think that's the thing that has stood out the most to me as a problem.
Yeah.
One spike doesn't bother me, but this constant high level, it's pretty terrible for subjects.
So for cutting stuff, I might also say that T1, 2, 3, 4 stuff felt to me a bit too distant to like just talking about motion correction. I mean, I see that you are talking about some partial volume effects like white matter gray matter boundary shifting around, but also like you spent quite a bit of time to like bring it to that point, right? And it's not directly related.
Yeah, thanks. To distance. I get nodding here. Peter van Garen, you do a kind of prospective motion correction. Do you feel ill-represented? I know you don't use it for high-resolution fMRI, but do you have comments of something that I missed? I think I might be. He might have his audio off. Yeah. Okay, maybe I approach him personally. Yeah.
Oh, he doesn't want to.
Yeah.
I don't have a time cutting one, but you talk about the cool concept of like the higher resolution being better for the motion correction. but you don't then, and you show like the residuals there that they're lower in the
Right.
graph. But then at the end, you show like different actual brain images as the result of the motion corrections, but you don't show it. Like you don't show an upsampled version. Like, you know what I mean?
So, you mean at the simulation, like at this one?
So yeah, you do all that simulation, and then I think maybe, I can't see the slide. Yeah, I think to the left, right, that thing.
That, no way.
Somewhere you're showing like the final result of the motion correction.
Ah, that one. Yeah, it's hidden. It's that one.
At 19, or are you talking about?
Yeah, maybe this one. Well,
On the bottom left is the motion corrected one.
I don't think it's this one. Somewhere I thought you're showing a comparison of your motion corrections.
You mean the estimation, that one?
Yes, I guess, yeah, and then you go in and say, yeah, and you're saying, the higher resolution is better.
Right.
But I guess you don't show like a final version of like the practical or the final result of it, like showing that it's like the image quality looked a little, or the motion,
Right. When
it did a better job.
Right.
in your-
you mean like a movie? I like those
Yeah,
movies too. Yeah.
All your
Yeah.
movie wiggles are like for regular
Right.
like
Right.
not the very
Right.
high resolution.
Yeah.
Example.
And this is not my study, but I think I can easily do the same thing and create a movie. Yes, that would be more intuitive than a few bar graphs. I just copy pasted the figure from the paper. I think.
Yeah, I think so.
Yeah.
I think it just drives the point.
Right.
For me.
Right.
Because it's really cool.
It also crosses my mind here that you may want to, I don't know if you want to hide something from their figure, because they do the upsampling, right? Their claim is that upsampling is even better than staying at your original high resolution.
Right.
And I don't think you talk about upsampling at any other point.
Mhm.
You talk about not being able to get data, you can't get better than you had.
Right. Yes.
So I don't know if that's something you care about. It kind of made me think you were going to
Right.
talk about doing some sort of upsampling, because
Right.
you talk about that on your blog. But
Yes,
minor
and
point.
Valentin Kemper had proposed it. I'm not unsure about it. I don't know where I stand. Like, because at the end, upsampling and applying a kind of a linear resampling is kind of equivalent to just using not a kind of linear resampling and using a kind of sync interpolation in my head. So I'm not really, I don't really understand the benefit of upsampling as I proposed it, or as other people proposed it. So and these are also slides from like Jonathan. Yeah, maybe I should come to my own decision and then I don't know. What do you think? Do you upsample? It's very annoying, right?
Frequently, yes. I think about it in the context of preservation. Obviously, you can't
Okay.
create, but you
Right.
can preserve. But that's kind of your point about sync versus linear. If you
Right.
use, but I guess there has to be a crossing boundary. Like if you upsample twice and use sync, you're probably great. If you upsample twice and you use linear, you're like sync with regular. I'd prefer if we never had to upsample at all, because everything just starts taking too long. But
Yeah. It's easy to test, I think, also. And maybe this question will come up, so maybe I should be prepared. Farouk, what's your opinion? Does upsampling help, or is it the same as sync?
Well, theoretically, it must help. It will help, or it is going to help. I don't know how more strongly I can say it. But the way I think about it is the following: like the problem is estimation. Sure, you will have some estimation error, and if you have high resolution data, your estimation will be better. Fine, this is okay. The other problem is the resampling. So imagine like just the same image, then you resample it in place 100 times, like iterate over. What will happen is that you will start seeing the image dissolving or like getting blurred because of just the interpolation that you are sampling. Like when you, even in place, when you resample data with trilinear sync, whatever, you are incorporating information from the neighboring voxels into the same voxel and like resampling its value. So basically, like any resampling works as a diffusion process in a general way. The more you do it, the more diffuse your data will get. So therefore, one way of dealing with it is to upsample at the beginning, nearest neighbor I would prefer, and then which like doesn't create anything new, also doesn't mix voxels. And then when you apply this to with a new like a grid through some resampling, you will induce less diffusion. So you can actually state all this problem as a like a diffusion problem. You are trying to minimize local voxel to voxel diffusion that you induce to your data. But usually at this point, I think I didn't see anyone who understood me. So that's why I did those animations that you show. So therefore I think, I mean, I don't know what I say. Yeah, it's like it's hard to upsample the data. It's a lot of time. People don't want to do it. I am not fully convinced that if you upsample a lot, it will give you all of a sudden like some layer that you wouldn't see otherwise. So that I am uncertain. But does it help as a like a theoretical problem, like a question, you know, to preserve the data? Yes, upsampling helps. If you do nearest neighbor to me. I don't know. It's like a very nerdy discussion. I don't think anyone cares about this, to be honest. Like,
I think it's easy to test. Yeah. Yeah.
I care a lot about this. And personally, the intuition is obvious to me of why the upsampling has to help theoretically. But then I wanted to keep this for later, but at the end of the day, if you want to talk about motion holding us back or not holding us back, there has to be, in my view, some kind of clear-cut ground truth that you're either recovering or not recovering, or better or worse. The way I see the development of the talk is like everything's super useful and interesting. And it says about a lot of things that can be done to mitigate motion. But it doesn't tell me anything that convinces me that the motion is not holding us back, or why I should think that. So that was sort of the thing I want to say later, but I said it now, because it relates specifically to this point. Well, how diffusion processes or problems in alignment, in the end, limit what you can resolve and what it is that you want to resolve. So an answer to that would be like convincing me whether these things are limiting me or not, or when they will limit me with respect to what questions. But in the end, the conclusion is like motion is not holding us back.
Right.
And I don't see anything that convinces me of that thing.
I mean, it's an annoyance. That's what I say.
But why should I believe that it's not holding me back?
Well, there are other issues that hold us back more than motion. That's kind of in the conclusion.
Okay, because
And I don't talk about those.
but sort of the way I read it is that you shouldn't worry so much about motion.
Right. Because kind of I show examples where kind of to give a feel of kind of how annoying is it, right? Is it something that doesn't allow you from doing your study? I don't know any study that kind of was discontinued because a motion couldn't be resolved.
Yeah, but that's
Right.
like a sociological argument in my view. What I would like to see is, okay, you wanted to recover ocular dominance columns or something like that, and there was a negligible difference between, you know, worrying so much about it. You should have worried about something else, which is a valid point.
Right.
But for me, I don't see the argument laid out in the talk.
I mean, with
You know what I'm trying to say? Maybe I'm wrong.
Kind
Maybe
of.
I missed it.
like you see a lot of examples where you see that you can resolve a lot despite motion. Like in this example, there's a lot of motion and you still see stripes. So therefore, all the motion that was more than the spatial scale of those stripes was not keeping me from seeing those stripes.
You never think, I guess, Fernando, are you talking about just the effect that it has on your statistics, like just making that explicit link?
Yeah, or when you really know that there were stripes there for sure. So therefore, look, there was motion, I could recover the strap that I know for certain that they were there.
Like showing like a low motion, like a run that's much lower motion, and saying here are the stripes. Now here's a high motion run corrected, and you see
Yes,
those-
or for example, but it's just that I feel like the ground truth and some kind of measure of how much this was a problem compared to other things, that would be kind of great, you know? Like some comparison of the scale of what this is relevant compared to other problems. So maybe refocusing the attention of the bigger problems is like super important. But maybe to forget that this can be very important with specific kind of question can also be good to keep in mind. But I don't know, maybe I'm just kind of.
I mean, with motion, it's very hard to have a ground truth, right? And you cannot repeat it kind of with perspective and without perspective to have the same motion in there. So the kind of the few studies that exist, and there are like almost none, as I showed, like is the one from Wang et al., where they basically downsample the data and then repeat the retrospective motion correction, and then say it gets worse the lower the resolution. So kind of the proof it doesn't exist.
Exactly. So essentially, we don't know.
Well, we do compared to other fields. We don't have, we can still use high resolution fMRI, whereas other fields, for example, the presentations before me, they will say you can never ever do your kind of 0.2 whole brain structural scan, which takes 50 minutes without prospective motion correction. They have this proof that without you can do it. We don't have this proof. So it's not, there's no proof that it's holding us back.
Okay, I see. I see. I saw it more like there is proof that it's not holding us back. And I didn't see that proof. You see what I mean?
It doesn't
I don't know
exist,
the
yeah.
context of the other talks and things.
I mean, like a long time ago when we were checking the GE prospective motion correction, like we did these studies with Joelle. She's the lead author on that, where you know, you fired a scan where the subject was perfectly like as still as they could be, one where they were moving, but you turned off the prospective motion correction, and then finally the third scan where they were moving again, but you had prospective motion correction turned on. I think that's maybe what, you know.
Right, they would need for fMRI, yeah, for high resolution fMRI.
Yeah.
Yeah. I mean, there are a few counterexamples, not in the high resolution domain though, like that people do like wiggling task of the toes, and then they see you have false positives in the brain if you don't turn on prospective motion correction and you don't have them. So in those cases, the false positives are like there and you can only get them away. But this is a kind of at low resolution. It's not for high resolution. So it's unclear how. There's no proof.
So I didn't fully hear the discussion, but did you and like I mean people there end up saying that motion holds us back to go for higher resolution in anatomical?
No, I think Fernando was making a point that there's no proof that it doesn't. And I said
proof
there's
that
no,
it doesn't. Okay.
so I cannot prove that it's not holding us back. Like I cannot prove my statement that I say it's not holding us back. I think what I can say is that I don't have direct proof that it is holding us back. So
yes, okay.
So I'm kind of leaving it out there. So my claim is kind of too strong, maybe.
And it's twice in the conclusion slide. It says twice that it's not holding us back, given that it's.
And the other one is for the future, that it says it will remain an annoyance.
And will remain not holding us back.
May I ask a question? I'm online.
Oh, yes, please.
It's an issue of, I have noticed that when people are doing multi-band acquisitions, that the higher the multi-band, the factor, the image becomes a little bit more blurry. Is that because there's an augmentation of the effect of motion? Why is that happening? I can't understand that.
Increased G factor.
Right.
It's just getting noisier and blurrier.
You heard what Vinay said?
He was very faint.
Okay.
I'm sorry.
So he said that the higher the multiband, the higher the G factor. So the kind of the noise amplification, which is because it's G factor, it's very smooth because it's a small grappa kernel, it's smooth in image space, therefore it kind of looks blurrier. Because the noise is kind of increased. I think there are many angles on this. Like there's more kind of signal leakage across slices, which also might make it look blurrier. There are these kind of low spatial resolution kind of shading patterns that might make it look blurrier. Overall, I think it shouldn't. But in the model of how SMS works, and there could be noise amplification and signal leakage, but it shouldn't kind of be a Gaussian blurring to that degree.
So how does one deal with that? If I do the motion correction, should it get better? Should I try to do it on a higher, do the fMRI acquisition on a scanner that gives me a better signal? How do I deal with that?
Well, at the end, I guess motion correction will not help with the blurring that I think you're describing, or kind of being rank deficient with respect to the number of coils and the amount of acceleration you do. There's a limit of what you can do in multibanding, given that the hardware that you have, and and how much you want to push it with respect to SNR. And if you go easy on multiband, you will not have this issue as strongly, I guess. Motion correction, I doubt will solve for it.
Okay, great, thank you.
I have a question about since people are using multi stuff now. So I think multi-echo recording can be used to eliminate motion effects because motion is insensitive to, or multi-echo is kind of whatever, insensitive to motion if you use all the echoes. In Vaso, do you use one echo or multi-echo?
You can use whatever you like. With high resolution, it's very hard to do multi-echo. Let me start by confirming, I think, what you're saying, that when there are spin history effects due to motion, multi-echo API can account for that because it's using the pure T2 star and can look at the kind of zero effects as opposed to the T2 star effects. And that's really a component, one of many, that you need to deal with when you have motion that can be accounted for. In these high resolution experiments, there's almost nobody who can do multi-echo. And those people who do multi-echo and publish something have TRs of 60 seconds, so which puts you in a very different regime of motion sensitivity. So yeah, absolutely, you're right. For conventional fMRI, motion can be dealt with to some degree with multi-echo. For the purpose of this talk, yeah, unfortunately, we can't do multi-echo easily. Head gradient, you have a nice saying, head gradient, yes. Yes, head gradient. Segmentation might help too, both.
There is some idea that you could use the, what is it, the warp kit, the multi-echo TR by TR distortion correction approach as a ground truth validation for the nonlinear method. So yes, I don't know how you get multi-echo data to be reasonable TR at high enough resolution to tell a good story. And I don't know if you need all three echoes. It might be sufficient to have two.
Or EPTI. Yeah.
Oh yeah, or EPTI would be. So at least with that approach, if you have the phase data and you can deal with it correctly, though, you could get an estimate of the TR by TR distortion, and that would, I mean, it's closer to ground truth than the SIN estimates would be, but you can at least compare them.
Right. Even, yeah, like you're referring to the B0, like the higher order nonlinear motion that you have. Right.
Yeah, like using SIN to do within
Right.
volume, within run motion correction. Because it's also just computationally.
And I think had a paper once doing it with single echo, right? Getting the B0, getting a field map. Yeah. A lot of cool things. Yeah.
Hi, Renzo. So I also tried to reduce the motion with Masaki a few days ago, and I think you maybe know that there's has a group they used create a subject-specific head case during the scanning. Do you think that would be useful, or do you know any group use that for their function model?
That's a great comment. If you have any data about that, or maybe just a picture with the person in the head case, could you send it to me? Then I would include it in my mitigation slide. I think there was a GitHub for it. We had it, Sean Merritt had one and wanted to establish it at NIH too. Like these molds that are kind of based on the skull, which I think if you don't have too much hair can restrict motion, but also I think for Tyler, she was interested in kind of multi-session stuff and might use and propose that kind of approach. Unfortunately, the company CaseForge went out of business. So if you want to do that, I guess that's what Hiromasa is referring to, is kind of you need to do it on your own. You need to have a workshop or
Yeah. I was
yeah.
I just trying to buy a 3D scanner, and you can use a swimming cap, and you can have a very high resolution head model. Then you can make that kinds of case. I will send the link to you.
Thanks, appreciate it.
And
Yeah,
probably I can try it before the summer, and if I have some good result, I will let you know.
thanks. You don't need to have data, just an image that I can mention it would be cool. I couldn't find it. Yeah.
Sure.
Okay. Okay. Cool. Thanks. Okay. All right. Are there any other comments? We have to. Thanks.
I just found the link from the GitHub, so you can find.
Thanks. Oh, it's on the other. Thank you. Appreciate it. Yeah. All right. Thanks, everybody. And see you in 2 weeks with continued rehearsal presentations. Bye-bye.
Thank you. Bye.